Hello, everyone. Good afternoon, good evening if you're in Europe, good morning, and good midday, I guess, if you're over across the pond, or good night, wherever you are. Um, Thanks for joining our latest DevNation with our special guest today is Hans Peter. Hi, Hans Peter. How are you?
Hi, I'm doing good. Thanks you for hosting me today.
Thank you. Thank you. So today we're going to be talking about event-driven architectures, right? So we have three different patterns that you're going to tell us about. So I can't wait. So I don't know if you want to maybe introduce yourself first.
Yeah, let's do that very briefly. So my name is Hans Peter. Hello, everyone. I joined Red Hat last summer as a developer advocate. I'm working actually in the same team. We are a team of global developer advocates together with Kevin. And I've done a couple of things in the open source communities related to actually the contents that I'm going to share with you today. So I'm very interested in event-driven architectures, in stream processing, and a little bit of data engineering too. And I'm looking forward to dive into today's topic. And with that, I think we can already do that and get this going. We have quite some ground to cover. So let me briefly show you the agenda. So first, just to set the stage and get everybody roughly on the same page, I plan to at least clarify what I mean with event-driven in the context of today's session. Then we're gonna, of course, talk a little bit about events. Without events, of course, such an architecture wouldn't be possible at all. And then we switch over to the main part where I'm going to walk you through the three patterns, namely the claim check pattern, the content enricher pattern, and finally the message translator pattern. And I'm going to explain those. I'm going to try to also make the case for which are the challenges that they are trying to help us with. And then the idea is that we also deploy demo scenarios and see this in action so that we can explore that together a little bit more closely. Talking about demos, I am going to do the demos and deploy the things today on OpenShift Developer Sandbox. And this is, in fact, an invitation to all of you who are joining today. If you want to try out enterprise-ready Kubernetes in a fully managed cloud-hosted way, then please feel free. You can find the short link here on that slide. If you go there, all you need is to register a Red Hat account. So you don't even have to have a credit card or anything. So there's literally no catch. And once you register there, you come to a page where you can basically start and claim your own personal sandbox, which gives you this enterprise-ready Kubernetes environment that I'm talking about. And usually there is an SMS verification step, which you can circumvent by using the code that is on that slide as well. And again, you get your playground for enterprise-ready OpenShift for 30 days with limited resources. But as you will see during this talk, you can do quite a bunch of interesting things. And it's a great playground to learn about Kubernetes that way. I'm going to show that to you also towards the end again, so no worries. You can then, together with the repository that I will also point you to afterwards, try out everything at your own pace in the convenience of your home. So let me start by doing this brief clarification of what I mean when I say event-driven architectures. Now, there is multiple definitions out there. I'm not a big fan of definitions, but here, at least, what I try to do is summarize the main characteristics that event-driven architectures are about. So obviously, we use these to have looser coupled applications or services. We try to model all our communication needs between those applications based on the sending and receiving of events. And for that, we don't want to do that in a point-to-point fashion. We want to use some kind of messaging infrastructure, an event streaming platform, for instance. And in fact, today, because this is where I come from, this is where my background is, we're going to see that based on Apache Kafka. So what I mean is basically this illustration that tries to depict roughly what we are going to look into today, which kind of event-driven architecture we are aiming for. So there are services, and usually you have event-driven architectures very often these days in the context of a microservices architecture. And then you have multiple services which are depicted here, and they can act as producers to send and create new events. They can act as consumers, and many times, I think more often than not, they are doing both things. They are sending events, they are receiving events, and in return, as a reaction, create new events. So again, we have some kind of event backbone here, and this can be an event streaming platform. So some kind of durable log, and in our case, it will be Apache Kafka. When we look at that, the flavors of event-driven architecture that I'm going to refer to here is that of event notification mixed with a little bit of event-carried state transfer. This is what we are mainly talking about for the rest of this session. Now, that illustration, of course, I'm very well aware it's in one to some degree terrible, because it's a significant oversimplification of any kind of real-world system that you would have. In this case, it's the e-commerce domain, but still, I think it captures at least the essence nicely, that what we want to achieve regarding an event-driven communication model here. When I say these two flavors are mixed here, event notification and event carried state transfer, there must be more, otherwise I wouldn't say it like that. And if you're interested to learn about other flavors of event-driven systems, I can highly encourage you to look at a pretty popular article written by Martin Fowler in that context, who additionally describes two further event-driven architectural styles, namely the event sourcing model and CQRS, both of which are, in my opinion, more complex and also not that often found, at least not that broadly applied in the wild, in my experience. So if you want to know more about these, check that out. We are going to focus on the other two, event notification and event carried state transfer. Now, irrespective of the flavor, we wouldn't have any event-driven architecture without events. Those events are flying around everywhere in such an architecture, and this means we should at least briefly discuss which kinds of events there are, how can we design our event payloads, what kind of data do we put into these, and things like that. And let's briefly do that. So very basically, what we do with events is we use events to communicate the fact that something has happened somewhere in our system. Now, this is very generic. Now, hopefully, this something is some kind of business relevant fact that we want to notify other services in our architecture about. And so we could, again, take the example of an order service. And at one point, we could say, well, we create order-created events. We produce those. Now, this would be, in theory, a valid event. But of course, it's one of the most awful ones in terms that this event is anything but useful. The only thing that you could do with such an event is basically teasing any interested downstream consumer about the fact that orders were created, right? So at the very least, what we should put into an event is always some kind of unique identifier, which allows a consumer to take action and ask back to the originating system for additional data. Now, we can, of course, then, this would be what you do at the very least for some kind of event notification system. I'm aware that you might want to have timestamps, you might want at least some metadata to know the origin of that event and things like that, but related to the order, it could only be the ID. Now you start to think of, well, maybe it's useful for consumers not to always have to ask back to put more stuff into. So you might come up with the idea to put product information into that same event. You might come with the idea to say, well, we need more details, so you put order lines in. You might want to put the whole amount in, and so on and so forth. And at one point, you might have quite a copious event, even with customer-related data, addresses, and things like that. So you might wonder, well, dude, take it easy, stop it here. And this would be really a valid reaction, because the question here is, where does this end? when should we stop putting ever more pieces of information into an event payload. And that's in fact something for which there is unfortunately neither a single nor a simple answer. In fact, we should be mindful about how we design those events, what main purpose they should fulfill. And this is what we do with having consumers in mind. We want to create events that are useful to at least a certain subset of our consumers in the way we design them today. And there are multiple ways to look at that, but I want to share at least 4 categories of events with you. The first is a notification event, pretty much what we had at the beginning of the previous slide. If we look at orders, it would be an order placed event with just the ID and maybe some timestamp, metadata. But related to the order, we would only have the ID. And a completely different approach would be that of a state transfer event, where you try to basically encode the whole state of one of your entities in your domain and put it into an event that you can transfer to some other systems, together with metadata, together with potentially schema information and things like that. Then we have domain events. And as the name implies, the main difference, irrespective of the content, is that for domain events, we usually have the semantic that they should stay within their bounded context. So domain events, other than integration events, are not meant to be sent out of a bounded context. So if you communicate these, this should happen among services within the same bounded context. And finally, we could have something like delta events. When you think about state changes that you want to communicate between systems, you could say that you want to let another system know what actually changed. And you could do that in different ways. You could say you encode the full thing, how it looked before the change, or you could encode and then together with the thing, how it looked after the change, or you could just communicate this in a more lightweight manner by saying, well, I just put the delta, so only the fields that changed into this. So these are, at least in my opinion, very useful ways to think about how to design events. And don't be distracted by the fact that these are all depicted in JSON here. It can be, of course, any different thing. Usually you follow some common specification, things like the cloud event specification, and you can decide for how you want to serialize these events. For instance, in Kafka, you could say you want to build your events and serialize them with Avro, protobuf, or binary formats such as this, or you could say JSON or JSON with schema, and you have multiple approaches how to do that. So we might be tempted to think and seek for bullets of silver when it comes to the event design, but at the end of the day, all we will find is trade-offs. We should keep in mind that no matter how hard we try, we will never have the perfect type of event for all potential consumers that want to work with these. And even if we can do that today, we might have consumers tomorrow that expect something different. And now this, in fact, brings me exactly to the main part of today, which is all about patterns, because those patterns, to some degree, will help us to cope with these challenges, with these implications of the way we design events, and deal with those trade-offs that are here in a systematic and reasonable way. So first up is the claim check pattern. And the challenge we try to solve with it is the following. We might have an unnaturally large event, copious fat events. Maybe those events are even too large to be reasonably handled with the messaging infrastructure we want to use. And this can have multiple different reasons. And there are just 2 reasons on that slide here. It could be that we want to work with like inherently binary data, such as media files. And the other thing that we often find is that you have text-based formats, such as XML or JSON. But some fields there, they are actually embedding binary information by means of a base64 encoded data field. And so whenever you have that, you should carefully think if you really want to put all of that into your messaging infrastructure and send it around and have it replicated in your cluster and so on, because that can be pretty wasteful and also not very efficient, and also economically it could be a bad idea to do that. So the claim check pattern helps us with this and suggests to actually externalize large binary payloads into separate storage systems. So the idea there is we take the payload, we send it to some object storage such as S3 or MinIO or any kind of cloud object storage. And then we take just the identifier for that object that we stored in an S3 bucket and put it into the payload. And then we just send a very light event, namely some sort of identifier metadata plus the claim check itself that can then be used from consumers in order to load the actual data that has been stored for that reference. So here, the demo scenario that I prepared is in the context of a media processing pipeline. Now, it will not really be about processing media. It will just be about sending image files between multiple services. And we are going to do that by not putting those image data into our messages and store them in Kafka topics, but we're going to externalize these in an object storage. In our case, it will be MinIO, which is S3 compatible. A very quick illustration how this scenario looks like, and then we are trying to deploy that. So the claim check pattern here. We have a producer application written in my example here with as a simple Quarkus Kafka producer app. It generates images, or in fact, it just randomly produces images by taking from by choosing from 10 predefined images and sends those. Then the way this works here is that we use a special serializer for that message, and that serializer takes the responsibility of externalizing our payload into object storage. It will be MinIO buckets here. And then what we send to the topic is just this reference and some key identifier in addition to which in our case is just the file name of the image. And then at the consumption side, the consumer retrieves the message, retrieves the claim check that was transferred over the Kafka topic, and then it knows that it needs to take action, read out that image, the actual image data, and can do its task of processing images. It could be that it wants to detect faces in the image. It could be about some kind of image description, object detection, whatever it is that you want to do with those images then regarding your business logic. With that, let me go out of the slides and try to deploy that scenario. So we have here, I'm here in my project. I'm going to share that repository at the end of the session with you. And all of the things that we need to deploy that demo that we have just talked about is available as YAML manifests. So I will go there and just verify that my OpenShift sandbox instance is empty. This looks good. And then I'm going to apply basically this whole folder with all the YAMLs in it. And then let's see what we get from there. Okay. Let's give it a few moments and let's see. It now creates everything that this example needs, and we are going to inspect that then in OpenShift. Let me for that switch to the browser and let's see. Let me go to the topology view. Hope you can see that by now. Let me zoom out a bit and let me rearrange that slightly because it looks the auto layout is a bit hard to read. So let me just change that a bit so that we easier see what is going on and what has been deployed here. Let me now zoom back in again now that we have rearranged it slightly to see that better. So all of those components have been deployed. And here on the left, we see the application related parts which are implementing this claim check pattern. On the right, we see, I'm zooming in here a bit, we see the infrastructure components here. We have Kafka with Zookeeper, we have MinIO as our object storage, and we had just a job that initialized our object storage accordingly. So here we have our producer application. It sends image data, but again, it will externalize the large payloads to MinIO and then just send the claim check reference towards the Kafka topic. We also have a consumer which does the exact opposite. It retrieves the message from Kafka. It sees, oh, it contains a claim check, and it will load the data from MinIO. And finally, to contrast this with a normal consumer that has no clue about that claim check thing, we see what is actually stored in the Kafka topic. Let me briefly go into the logs to see what we have here. So what we see here is that the application here is sending image data. It sends different JPEGs. And again, the payload of that JPEG, the binary data representing the picture, is offloaded to MinIO. So it sends those images by randomly selecting from 10. So let's verify in the MinIO object storage if that actually works. And here I see that I will do one thing. I will create a route for that so that we can actually access MinIO. This is something that we have to do here. Otherwise, it's a bit hard to show that directly from the browser. So I will say this is called MinIO. I need this route. I'll just select the MinIO service we have here and then expose the port accordingly, as we can secure that because security is something we should always care about. And then we create that route. And what that route gives me is basically a public URL that I can choose now to access the object storage. Let me do that. So this is MinIO running here, and I'm going to log in real quick with admin and with the password. And once I'm there, I should see my bucket. And in this bucket, I have some folders, and here we see the images that have been written and externalized so that they are not part of our payload that we send to Kafka. Let me just take any of these, download them, to verify that this is actually working. I'm going to open that, and yes, this is some picture, and let's take another one, download it, just so to make sure that we are having real images here that are working. So yeah, that's it. So here are the images, and now let's inspect the consumer side. How does it look over there when we apply this claim check pattern? Let me go to the consumer side here, and let's verify the logs that are here. And here we see one thing. It retrieves a message. This is the file name of the image, and then it loads the image from MinIO, and it would execute business logic here, such as, like I said, object recognition, face detection, whatever it is that you want to do. And in case of an actual business logic, we just take out the characteristics of the image. We show the actual size of the loaded image and width and height, nothing else, just so that we have something to log here and see that retrieving the actual payload and the content of the image from the object store is working. Now, to contrast that with a normal consumer that has no clue about the claim check pattern, we just use that here to illustrate what a normal, in this case, the Kafka console consumer would see. It would see the key of the record, which is the original image name, and it would read as a value just the claim check reference, which is this S3 URL pointing to the actual image. Okay, so that's basically all I wanted to show regarding this claim check pattern and the demo that we have here. Let me go do one thing before going back to the slides. I will destroy all of that so that we have later a clean environment again to run the next pattern we are going to look at. Okay, so everything should be destroyed again. And yeah, that's good. We are good to go.
You're doing all of this in the OpenShift sandbox,
yes,
then, right?
Yes.
Wow. That's
all of that is running in the OpenShift sandbox, so it's completely free. That's why I said if the others want to explore it later based on the repo, you could do that and just claim that, and you can play around with it for 30 days. And after 30 days, you just renew it and you keep going and implementing and experimenting stuff. That's right. So let me go back to the slides and let's see what we can do about the next. So a quick discussion what we have seen. We applied the claim check pattern here in the context of Apache Kafka. We could do that pretty easily because a special serializer did all the heavy lifting when it came to externalizing the payload to object storage. And again, it's fine to use Azure Blob Storage, Google Cloud Storage, whatever you want to have. All of this works nicely. Now you might say, well, maybe I'm in a Kafka Connect context. I can't use the serializer there. There is a converter. And in fact, that converter is also part of this project, which, by the way, is a community project from from a company that does a lot of interesting things in the Kafka space, and it's also linked then in the slides, and you find it in the GitHub repo as well. So explore that if you need that, because it's really helpful. What we cannot do with that approach, at least not at the moment, is we cannot say we only want to externalize parts of our payload. So it either externalizes the whole payload. In this case, the whole payload was an image, so it was reasonable to do that, right? You would not like try to externalize half of your image. But for another text-based payload with embedded binary data in base 64, you could say, well, I'll keep all the fields in the payload and just externalize this one field. This would need some custom code at your end. Maybe you can also contribute that to the serializer if you want to. To some degrees, it's a dual rights problem. I just briefly refer to that. What that means is you could have the problem that the serializer successfully stores the image, in my case, in S3, and then later you fail to create the Kafka event, and the image would still be in your object storage. So that is something that I think you can live with most of the time. But what is guaranteed is that if you have written to Kafka, you will absolutely be able to reference that image, because that happened before that. So with that, let's look at the second pattern, which is the content enricher pattern. And here, the challenge we face is pretty much the exact opposite of what we just discussed earlier. So here we have very sparse payloads which contain very little information. Think about the most extreme form of a notification event, which just contains the ID. This would mean that every consumer would always have to refer back to the originating service to ask for additional data. And this is something that you want to avoid, because it, to some degree, destroys this loose coupling of an event-driven architecture by starting to do RPC calls in a point-to-point fashion to retrieve additional data. So here we have the challenge that we want to enrich events before they get consumed, but we want to do that in a separate kind of processing step, such that the consumer doesn't need to care and gets all the data it expects to and needs to do its work. So the idea is we take the original payload, maybe it contains just an identifier referring to a different entity in our domain, and then the idea is that this enrichment step loads the data somehow, does a join or performs a lookup, and then sends back this enriched event, so that a consumer can just pick out the event of our Kafka topic and be good to go. Here, the demo scenario is in the context of IoT sensor data processing. And the demo scenario is such that we have, again, an application that just produces random sensor measurements for certain device IDs. And then the task is that some consumers want to have additional device data, so metadata, giving further descriptions about the device that actually created or measured those values from its sensors. And we do that in the following way. Let me briefly again depict what we have here. Here we pretend that our device metadata is stored in a relational database. It's MySQL in this case. And we are going to feed all of this metadata describing our devices into Kafka. We use change data capture, and we use Debezium, which is, I think, one of the most popular and also really feature-rich open source technologies to do change data capture against various different data stores. So what Debezium will do is it will run in the context of Kafka Connect. We'll look into the database, do an initial snapshot of everything there is in this device data, send it to a Kafka topic, and then continuously listens to the database's bin log, in this case of MySQL, and stream all the changes that are happening to that data into the topic, so that we always have the latest state from the database in a Kafka topic. Then we have this producer app. It just generates random sensor data, in our case, for different devices. And now the task is that we come up with an enricher application that takes this raw sensor data stream and joins the metadata for devices against the sensor stream, so that we end up with an enriched payload that we see in the upper right here. That is then something that the downstream consumer can take without the hassle of figuring out how it can find the device data and augment the payload on its own. So here our consumer is not a real consumer in that sense. It's just another, in this case, sync connector that will take these enriched events and write it into a time series collection of MongoDB so that you can do a time series based analysis on that enriched events. Again, let me show that to you in action, and let's deploy this so that we have something live to look at. Sorry, that's the wrong window. That is what I wanted. There's what I wanted to go. So again, the same thing. We are in a different folder of that repository that I will share at the end. We are in the claim check pattern here, and I do the same thing. I'm going to apply not just one, but actually all the YAMLs that are in that folder here. And again, it will spin up multiple things for us and deploy a couple of pods. As we have done it in the previous example, I want to go into the nice web UI of the OpenShift console here. Again, just make sure that all of this is, I don't know what's going on here. All of this is depicted in an easier way. Now let's do it that way. It's fine. So above here, we have all the infrastructure components. We have Kafka, Zookeeper, we have Kafka Connect, we have our MongoDB database, we have MySQL, and this is what we need. And then we have the application side, this producer application that fakes and simulates device data being pushed to Kafka. And then we have an Enricher app. Let's see if both of these apps are already doing something. The sensor data app does something. Let me just briefly verify the logs if that's the same for that one. Yeah, that looks good. So let's see. First of all, what we have talked about, the device data resides in MySQL. A Kafka source connector using Debezium will read this data and will send it to Kafka here, okay? Because this device data will be needed by the Enricher app. The Enricher app takes that data and keeps it in its local state store. And every time something would change here, that change would be propagated so that the Enricher app always has the latest device data that reflects the state in the database. So this is a typical example, if you want to, of event carried state transfer. You have some state in one place and you transfer it to another service in your system, and that service keeps its own local copy of that state and maintains it. So this is done so that the Enricher application can then take the sensor data stream that is produced from this application, and then anytime a sensor event comes in, all it needs to do is simply join over the device ID that is also contained in this event payload from the sensor data stream. And this is how it works. So let's see what the application does. Here we have the sensor data simulation. You see different types of sensor data and measurements for different device IDs. So this is that stream. And then we have, and let me do that real quick here, we have here the Enricher app. And that Enricher app has, for every event it retrieves, let me stop the log that we can see it, every sensor data it receives, it will now join the device data with that based on the ID here, and it creates an enriched sensor data event and writes that back to a new Kafka topic. And we have that logged here. So we see now, instead of just the ID, we have the brand of the device, we have some GPS location where the device is currently located, and we have an active flag, together with all the measurements that came in from the raw sensor data stream. So this is how the enrichment works. And again, the enrichment is then, it's implemented in Quarkus as well, using Kafka Streams extension for Quarkus, and basically writing such a stream processing topology with Kafka, the Kafka Streams DSL is not much of a big deal. You can inspect the code later on in the repository. I think we don't have the time to investigate the code for all those components in this session today, but I encourage you to give it a look if you want to learn how this is actually implemented behind the scenes. Let's see if this end-to-end flow is working, because remember, what we wanted to achieve is that these enriched events are eventually find their way into our MongoDB's time series collection. And the way this works here is that we have a Kafka connector, a sync connector, which takes these enriched events and writes these into a MongoDB time series collection. Let me go to that instance real quick, because here I can show that to you by going into the terminal. So I should be able to log into that database instance here, the Mongo shell, and then I use the database that was created. It's called IODDB, and then I always forget how the actual collection is called. It's called sensors TS. So we are going to take that collection, db get collection, I should be able to type correctly, sensors TS, and then we say find one. And this gives us just one such document that represents that enriched data. You now see nicely here, these were the raw measurements just with the ID, and now we have the location and the brand and the active or inactive status of a device, together with the timestamp when that event was created. And now you could start doing time series analysis and incorporate brand information and geolocation and do all sorts of fancy analytics on top of that enriched data. So this basically concludes that demo scenario that I wanted to share with you in this regard. Let me again do one thing. I will, because otherwise I forget, I will again delete all of this so that we later can work with our fresh namespace for the final and third demo that I prepared. Let me delete all of that stuff again. It should be gone now. We are clean again in our namespace here, and that's good. With that, let me switch back to the slides. So again, a quick discussion. In this case, we have seen that we could implement this content enricher pattern idea using a separate application, a Kafka Streams application, which was written with Quarkus. I would definitely encourage you, it doesn't really matter. You can use different technologies. If you don't want to use Kafka Streams, you can use, I don't know, Flink, or you can use Spark Streaming, or any kind of tech stack is fine, but I would definitely recommend to use a stream processing library and not try to do this by using a plain consumer or anything like that, because whenever you have that need of doing replicating some local state into an application's local state store, and when you want to do stateful processing like joins, or maybe you want to even do aggregations or windowed computations, this would be a nightmare to manually code without any capable stream processing framework. Alternatively, if you're not so much into programming, that's also not a problem, because many of these stream processing libraries have SQL abstractions. So you can choose to do these joins and enrichments, and at the end of the day, very often we are talking about just joining things or aggregating, grouping and aggregating things. And you can do that nicely with things like Flink SQL or Spark SQL or also KSQLDB. So there are a bunch of different SQL wrappers which allow you to do streaming SQL also in a stateful manner and do these enrichments. And then your enrichment app becomes basically one or a couple of SQL queries. And you don't actually have to code that application and compile it and deploy it in the usual way, but you can just send your SQL statements to some processing nodes, and they can do that step for you as well. So the enrichment should be kept separated from the consumer. This is what we have done here, and the reason for that is pretty clear. Chances are first and foremost that you might have multiple consumers that want to work with the enriched data, and also keeping that separate from the actual service that wants to work with it and then apply some various kinds of business logic on top of the enriched event is a separate concern. And so it makes a lot of sense to keep that separated from a coding perspective and deployment perspective as well. Yeah, with that, let me come to the final one. And this is the message translator pattern. Now, the challenge we try to solve with this is the one that sometimes we have to deal with either inconvenient payloads or simply incompatible payloads. Think about some kind of legacy system with a proprietary data format, and it doesn't make sense that all your consumers that want to work with the data try to understand and are implemented against this proprietary legacy data format. So very often it's a much better idea to say, well, I include this translation step, and ideally this again step happens somewhere in between, so in flight, so that your consumers don't need to deal with weirdly structured event payloads and are not coupled against that probably legacy event style or some kind, because when you do event-driven things, your event payload basically becomes your API. So that's the important thing to keep in mind. And you introduce then a lot of like coupling towards one particular format. And this is where message translator pattern comes in. And the idea is that you use it to make a bunch of modifications to your event payloads in flight. Maybe it's just tiny bits of changes that you need to do, such as data type conversions. Maybe you want to rename fields, maybe you want to remove fields altogether, maybe you want to mask sensitive data, maybe you want to encrypt fields, that's also possible. And you can even change the complete message format. Let's say you have your source is using XML or CSV and you need JSON on the other end, or the other way around, you have something in JSON and you need to bring it to XML. So also that is something that can be done in that translation step. Basically any kind of event payload modification, but ideally those are self-contained. And the reason why I'm saying this is that with self-contained, what I actually mean by this in that context is that all the steps that you take to modify and transform your payload should be doable by just taking the payload itself without doing things like doing RPC calls to different systems, or without like any kind of information that you would need to retrieve, or without trying to do aggregations in this step, because if you have that need, you are better served with what we have seen in the content enricher pattern earlier. So here you should take the payload and you should be able to work on that payload, and anything you can do without external additional help is fine to do in that step. So here the scenario is that of point of sales data processing. And the idea here is that in that demo, we have transaction data from points of sales, and they are in some storage, in some proprietary old CSV kind of format. And we need to send those to a web API, which expects a particular JSON payload for further processing. And again, what we do here in this scenario is we set up a streaming data pipeline without any custom code. We are only using Kafka Connect, the functionality of connectors and in-flight transformations that we get by applying so-called single message transforms. This is again some concept that we have in Kafka Connect. But again, these are just like examples of how to implement that. All of that can be implemented in various different ways with all the tech stacks that you like, but I just needed to choose something also for the demo. So here we are. We have CSV files stored somewhere with some kind of representing point of sales data. We then will run a file source connector. It will read CSV files. It will watch a folder. So every time a new file comes along, it will pick it up, and it will then line by line process these CSV records. And what it does is it will apply field renamings, that it will parse numeric information into proper numeric data types. It will also drop some fields that we are not interested in. And finally, it will serialize the events into a JSON payload and send that result of all those transformations then to the Kafka topic. And from there, we take it, again, without custom code, we apply a sync connector, and that sync connector reads those translated events and then has also the ability to batch a few of those together and forward them to our web API of the application that expects that point of sales data in exactly that format that we created by means of all of these translations that are happening in flight. So again, let me quickly spin that up, and that is then the final demo, and will also bring me then towards the end of what I planned for this talk. Let me go to the message translator pattern, and I'm going to apply here the folder, the whole folder in that part of the example, and then let me go to my OpenShift console again and see what we have here. So again, down here we have the infrastructure components, we have Kafka, Zookeeper, we have a job that is supposed to create connectors, and up here the actual message translation happens, and there is no application that we wrote. All of this happens with connectors, and except this fake target web service that just takes the payloads, the final payloads, and will log them. And let's inspect how the data flows in this example. Let me see first if the job did its thing. This looks good. The job realized Kafka Connect is here and instantiated the two connectors we are needing. So with that, we can go to, that was the job. Let me go back here to the topology view. We can go back and inspect very briefly just if the Kafka Connect thing is running fine. Also, that looks good. And so here, let me show you briefly the source, which is here on the terminal. Again, for simplicity reasons, that CSV file resides directly in this Kafka Connect worker, but you can imagine and envision that this is mounted from some kind of storage location here. And this is how the CSV data looks like. It has also, maybe it's more reasonable to look at the first couple of lines of that CSV file. And you see this has some particular naming for each of these columns, and this is the information that is represented for each transaction. And what we get out, and let me just run that real quick. I'm going to copy the command here real quick so that I can show you how the steps that happen in the message translation, how they change the payloads when we retrieve them from Kafka. So for that, let me quickly go to the Kafka node directly, because we don't have a better pod running here to show that. I go to the terminal again and inspect the Kafka topic, what it receives. So directly on that node, I should be able to read from that topic. And here it is. We see this point of sales data now with completely different names, with proper data types, numbers being real numbers and not just strings. We removed some fields, and we have what we wanted, also a JSON payload available now. And again, now the sync connector's task is to listen to that topic, to batch up to 10 of these. I just chosen 10, it can be any number. We wanted to batch multiple together so that the processing towards the web API is a bit more efficient than sending each and every single transaction in a separate post request. And if we take a look at this Quarkus application again here, it receives all those payloads in batches of up to 10 transactions. We see that in the logs, and it's already done. It's in total 10,000 transactions, roughly 1,000 log lines with 10 of each, meaning all of those will be there. You see sometimes we see less than 10. This is just because the batching happens such that it's not always exactly 10. It's up to 10. It's never more, but it can be less that we put in a patch in that regard. And again, the sync connector does that for us without any additional code. And here we have those just the log information of the transactions that were received. With that, I am about to finish. Let me just go to the slides one more time, and then we can open up for questions. So we have seen, again, an opinionated way to implement the message translator pattern. I have done that with Kafka Connect, meaning by configuration only. There is no code for the whole data pipeline. The only code we have is the one that simulated this target web API that we wanted to send the translated payloads to. We did all of those translations on the fly by composing multiple so-called single message transformations that are available in Kafka Connect. Another important thing to keep in mind is you can apply the translation on either side. So we could have also said, no, let's put the CSV data into our topic and let's do the translation on the other side of the data flow. Would have been an option. But in this case, it made more sense to do it before the data actually enters our messaging infrastructure. One thing to note here, if you go down that route and with this particular tag, you cannot do, and it's not because it's not supposed to do that. Whenever we talk about Kafka Connect and single message transforms, they are called like that because of a reason, namely that you operate on single messages only. So if you try to do some aggregations, windowing, or anything like that, this will not work in that step or in that way. For that, again, you would fall back to stream processing things with libraries or SQL wrappers. So let me wrap that up real quick. The summary of observations for that talk. We have seen that event-driven architectures can help us to define loosely coupled data flows. We get better extensibility. We also get higher degree of independence when it comes to working with separate services and apps across that landscape. We learned, hopefully, that good event design is vital. It needs collaboration across teams, and the domain expertise is also something that you will need. Despite that, there are no silver bullets for doing event design. It will always be about trade-offs, and we have hopefully seen that patterns such as the one that I've showed you today help with the implications and deal with the trade-offs. So here is the link. This is the link if you want to try out the examples on your own. You can go to that short URL. You find the GitHub repository there. It contains everything. There is a README. You can run those. And again, if you want to try that like I did today and deploy it in a Kubernetes environment, I invite you to, again, explore the OpenShift Developer Sandbox. Use this code here. Use this short link. It brings you directly there. Claim your sandbox, and you get your managed enterprise Kubernetes platform, which allows you to try out all those things. Okay. For those of you who haven't seen the link, let me go back. It's red.ht/eda-patterns, and this brings you to my public GitHub repository that hosts all of this. With that, I am basically done. I thank you a lot for joining in today. I hope there was something interesting for each and every one of you to take away from that talk. It was, I think, hopefully also nice to see the things in action, and gives you a chance to try that out later from the convenience of your home. That's it for me for the official part, and now I'm happy to take questions. Maybe there were questions in the chat that I'm happy to take and hopefully be able to answer right now. So if my colleagues that are hosting the show let me know about some questions, then I try to take them and answer them.
Sure. So I see we have a question. Is there a way to learn quickly about event-driven architectures? So are there some resources out there that can get them up to speed?
Yeah, so like I said, so first of all, if you are completely new to event-driven thinking and systems, I had one reference there that gives a good overview by Martin Fowler to understand, like in a technology agnostic way, how event-driven systems are supposed to work and what different types of event-driven systems there are. We looked in just two of them. And then there is, there is a bunch of good resources out there. If you just it depends on if you are more the reading type of learner, or if you want to learn those things more by watching videos. I think there is plenty of good stuff out there. We will share the slides, of course. And also we have, if you go to redhatdevelopers.com, we have also dedicated pages that you can look at. For instance, let me see, we can, if I can do that real quick, I can open that link here. We have a separate place also under Red Hat Developers to learn about that with, again, many things to read, many tutorials, many things to learn about right here, and explore.
I'll share the screen again because your screen wasn't shared anymore, but I shared it, and I posted the link as well.
Thank you. Yeah, this is a good page if you want to learn about multiple things, also regarding Red Hat offerings and how you can do that on OpenShift. And again, it depends on if you're looking for something that is more like the concepts and the generic side of things, or if you want to, if you're looking already for a particular technology. Let's take other questions.
Okay, I'm gonna unshare your screen and then let me know if I need to share it again. Okay, so the next question is, let's say a consumer gets a message from Kafka, but this consumer fails connecting to an external service to do a message enrichment. At this time, the received Kafka message was lost. So can you give us any point of advice or best practices about handling these kinds of scenarios?
Yeah, so first of all, it's you never lose a message in that sense. That's an important differentiation to make. For Kafka is a durable log, so messages stay there when they are consumed. So you can have 100 different applications that all consume the same events if you want that to happen. So it's not like a typical message queue where you would have usually one processor, and then the message is gone. That's very important to keep in mind. So messages are stored and you can decide for how long. And then a consumer decides itself. Kafka doesn't do that for you. You decide if you have successfully processed a message or not. And if you have done that, you would commit a so-called offset and to store the fact that you have processed a particular or messages from a particular topic partition up to a certain point. And then you produce the next and the next, and you can decide when you acknowledge and commit your offsets. So that means you can have a situation when you commit a message and then have a problem later, and later say, well, I have done that already and I need the next. Then you would, this one application would have skipped that event because of a failure. But this is then because you decided for that on purpose. So usually you use that in a way that you exactly know when you are fine, and before you are fine, you don't commit your offset to record the fact that you have processed a message correctly. I hope that answers the question.
Excellent. Thank you. So I don't see any further questions. There was a question at some point about what happens if your sandbox, like after the 30 days. And so basically I answered in the chat, but, maybe to give a little bit more context. So basically you get a sandbox for 30 days, after which it does get deleted.
Yeah.
You can start up a new sandbox if you want, and you can actually export all the things that you had in your sandbox. It's called GitOps Primer. And you can export all your resources, and then you can import them in, maybe another OpenShift that you started, or if you want to do another 30 days in the sandbox, then you just kind of can transfer them that way.
Yeah, exactly. I have not much to add that, except one thing. First of all, you get a notification email that this will happen, I think, in the next couple of days or something. So you get a reminder, hey, we just want to remind you in, 3 days, we will remove your stuff from the sandbox. And again, like Kevin said, well, first of all, the sandbox, right, is primarily for exploring stuff. You should not run things there that you are really dependent on for a whole year, right? And so when you think about what I did today, when you have all of your components in YAML manifests, you can just throw them away at any time and recreate them in your next sandbox. The only thing you would lose is state. So you would basically need to make sure if you want to actually save things that you wrote into a database or things that you wrote into a Kafka topic, yes, you would need to find a way to export them and back up those beforehand so that you can later restore it. But anything else, all the components that you were running, you are good to just recreate them automatically if you have all the manifests you need.
All right. Well, that ends our session. We're running out of time. Thank you very much, Hans-Peter. That was a really good session. I learned a lot myself, so that's great. Please stay tuned for what's next on DevNation. So we have DevNation sessions pretty regularly, so keep track of that. You can subscribe to our YouTube channel and join us on Slack as well, where if you have any more questions, then just post them there. We're always, there's always somebody around to answer those questions. Thank you all for joining, and see you at the next one. Thank you.
Thank you so much. Bye-bye all. Thanks for joining.